So before we also proceed, here is one important thing that they say. So you see, the ion is moving past, right? So the thing is, we're going to be integrating m dv dt all the way from t equals minus infinity to infinity. In other words, as the ion is very far from the electron, and after it's passed and it's gone very far away from the electron. Now, effectively, you see, the collision is only happening pretty much here, if you will. Okay, so the collision happens if you will, happens only when the ion is close to the electron. Right? That's obvious, right? So hence the definition of a collision, gosh, I don't know what's with my handwriting was never very good, but in this particular case, it's turning out to be a little worse than. So the collision time scale delta t is something like b over v. Okay, that follows just from this sentence. Okay, b is the distance of closest approach, and the ion is zipping past at a velocity v, and so it just follows that the collision time scale is something like b over v. This is something to keep in mind. We won't really use it in the calculations, but just keep this in mind. Okay, it's useful. So now again we are calculating the momentum impulse. Impulse rather, which is the difference in momentum before and after the collision, me delta v. And so in order to do that, you see right here, and so this is nothing but f, isn't it? M dv dt, this entire thing is nothing but f, right? So what you're doing is you're doing this. That's what you're doing, and you know what the f is. F is due to right here. This is f. So you plug it in. So that's what they've done. So this would be f, and you plug in. This is exactly this guy, right? You plug it in, and furthermore, you have an exact expression for x. It was written here, right? So you just plug it in, and then just be careful with the algebra, and it turns out that the only time-dependent part is this. The rest can be pulled out. Okay, and this is an integral that I'm sure you know how to do. Some kind of trigonometric substitution, and so you carry out this integral. T goes from minus infinity to infinity, and technically, I want to emphasize technically, t technically goes from minus infinity to infinity. Well, let's go ahead and I'll tell you a little more. Okay. So you carry out the integration, and turns out everything remains the same, and so the b comes downstairs. It's just a result of the integration, and this is how it turns out. And notice the perpendicular subscript in here. Okay, so delta v. So there is some further trigonometry here. Okay, is the perpendicular component of delta v. Okay, And perpendicular to what? Well, perpendicular to well, this essentially in the x direction, if you will, x or y direction. Parallel component would be z, and so perpendicular component will be anything that's perpendicular to z, which would be x or y. Okay, right. So I'm specializing to the perpendicular introduces one more, which is why you get the 3 halves. Okay, and not just 1 half. Okay, sorry, not just squared. This would be squared otherwise, right? So, but you know, if you do the trigonometry correctly, you will get this, and then you integrate, and that's the result. As such, the integral, yeah, it might take a little bit of time, but it's straightforward, standard stuff that I'm sure you've come across, so we won't bother with it. The important thing is to stare at the result and try to see what it says. And by way of an aside, they say that if you want to treat relativistic Coulomb collisions, you simply replace the mass by the relativistically correct mass, the gamma me. Okay, and so when v is very, very small in comparison to the speed of light, it just becomes me. When v is larger, well, you know, it is what it is. So it's just an aside. Now, right. At the moment, okay, note that the perturbation of the electron velocity is in the direction perpendicular to the. There is no component along the direction of particle motion. This is at least in this first order, where the assumption is that the particle trajectory is unperturbed. Okay, and it's unperturbed because the z component of the Coulomb force is an odd function of z or t. Very, very important. Okay. You know, now that I'm saying it, I wonder if there's an extra trig factor here, or at any rate, I urge you to. It's been some time since I've carried out this particular. I've done it a couple of times, but it's been some time. But I urge you to look at it yourself. But this is the main thing. Okay, the assumption is that the particle trajectory is unperturbed, and that follows from the way we've written down the Coulomb force also. Yes, because the z component of the Coulomb force is an odd function. So when you integrate over from t equals minus infinity to infinity, it cancels out. Okay, hence to this first order, there is no momentum loss, parallel momentum loss at least. Okay. Rather, a typical electron is only deflected by a very small angle, delta v perpendicular over, it's really tan theta. Tan theta is the perpendicular over v, but you know that for small angles, tan theta is approximately equal to theta, and so that's what it is. Okay, now let us skip this part. Let's skip this part for now, and let's just go on to, by the way, there should be a divided by 2 here. There's okay, there should be a divided by 2 here. Anyhow, yeah, so what we're doing here is simply energy conservation, right? So mv squared over 2 is equal to mv plus delta v quantity squared over 2 after collision, before collision, right? And you expand this and you get, you know, v squared plus 2v delta v plus delta v plus, so and there has to be divided by 2 simply because there's a divided by 2 here. Okay, so this is obvious, right? And you know the mv squared over 2 in here, they cancel out, and therefore you have the v dot delta v is equal to minus 1/2 delta v dot delta v. Okay, and we just said the delta v is essentially delta v perpendicular, so you might as well write this delta v dot delta v as delta v perpendicular dot delta v perpendicular. Okay, now what is this guy? Okay, the delta v, v dot delta v is the component of along V. Okay, that's what this is. And what would that be? This is essentially delta V parallel, because that's a definition, isn't it? Your ion is zipping along this way, so the change in velocity along the direction of V. That's what defines the parallel direction, the direction of V, right? So right. So therefore, we simply write this as delta V parallel, right? And of course, there's a V here, so you need to divide by a V here, and so it's minus 1 over 2 V delta V perpendicular times delta V perpendicular. That's delta V parallel. Okay, so I should have written V times delta V parallel. That is V. Like that. Okay, and so the delta V parallel is something that we're very interested in. Well, I'll tell you why. And so, but you see, the main thing the thing to remember here is that these are all small quantities. Anything that appears with a delta is a small quantity. So this is the small change in the parallel velocity, and that is equal to a small change in the perpendicular velocity times another small change in perpendicular velocity. So this would be, and all divided by V, of course. You see that the dimensions are okay. So this would be a velocity dimension, this would be a velocity dimension, and this would be, so the dimensions, one velocity cancels with another velocity, so dimensionally these are okay. All right. Now, you see, this is a small quantity, there's also a small quantity. So if this was 0.1, 0.1 times 0.1 gives you 0.01. So that's why this is what's called a first order quantity in terms of the weak Coulomb electric field. However, delta V parallel is a second order quantity. And they say it's a second order if you plug in for this delta V perpendicular from, what was this? From here, right? You just plug this in. You just directly plug in equation 2.4 in here. Okay, you just get this. You have a b squared v cubed. You see that, right? You get a v squared here, and because there's a extra v dividing it, you have a v cubed. Okay, and I wonder where the b squared came from. Yeah, well, yeah. So that's simply because of the two factors of delta v perpendicular. So that's where the v squared came from. Okay, and this guy, of course, goes away simply because cosine squared phi plus sine squared phi is 1. Okay, so there you have it. This is the yeah. So and Callan says that you can see that there's a second order term from the presence of two factors of 4 pi epsilon naught. That's one way of looking at it. It's also directly obvious. You have two deltas. Okay, so clearly the parallel impulse, the parallel velocity change is a smaller quantity than the perpendicular velocity change, simply because of the way we've set the problem up. Okay, by assumption almost. Okay, but this is just confirming the assumption. Okay, and yeah. Okay, now we'll go on. All of this is the same. Now, right. So you see, next, what? So this was one electron and one ion. Okay, what we did was one electron and one ion, and now what we will do is we will take a background of ions contained in a cylinder. Like that, okay, and we will integrate over the cross section of the cylinder. So this would be the cross section. Keep this diagram in mind. We'll come back to it, and so this would be the impact parameter B. Okay, right. So look at this, right? what we know, so you have a density Ni of ions, Ni ions per centimeter cubed or meter cubed. Okay, so Ni has the dimensions of per meter cubed, all right, and and cylindrical geometry, radius b, like we said. So this would be some kind of a dB. This little thing would be some kind of a dB, right? And what we are now going to generalize from the one electron, one ion result to a result where an electron is interacting with a host of ions, right? All contained in a cylinder. Why cylinder? Because it's essentially, if you are outside of the cylinder, the collisions don't matter. Okay, if you're well outside this, it's only within the impact parameter that it matters, right? So therefore, the number of ions passed per unit time is this. Okay, Ni times, and so Ni is per unit volume, and this is actually a three-dimensional quantity. This is a three-dimensional integral, because that's why it's written as d cube x. So you see, so the number per centimeter cube times centimeter cube, that gives you number. So number per unit time. Okay, so this is essentially number of ions passed by the electron per unit time. So this would be number per second, if you will. Okay, and the way you carry out this d cube x dt is this. What you do is you do a dz dt times integral dA. Okay, and this is how you find the cross-sectional, the dA gives you the cross-sectional area of the cylinder, which is, as you know, pi b squared, and this is how you get it, right? You do a d phi, a phi going from a phi, so this would be the phi, right? The phi going from 0 to 2 pi, right? And the b dB, which would be this, this is the b, and this would be the dB. This small thing, this is the dB, right? So so that's all really, and you can the dz dt is the v, right? By definition, because the ion is zipping past in the z direction, that was by definition, you see. That was by definition, right? It's traveling the z direction. So the dz dt is replaced by the v, and that's where this v comes from, and that's that. Okay, so we are now interested in finding out the average force in the parallel direction. Is a given electron slowed down or speeded up or anything as a result of this Coulomb collision? This is the question we're asking. Okay, and that is essentially this. Okay, but don't pay this middle step is not too important. Don't be confused by this, and I mean, and the fact that this delta t is something like b over v, as we discussed here. The collision time, where was that? Yeah, so the collision time is this. That we're not making any use of that. All right, we are simply directly plugging in this here, number of electrons per so the number of the number of ions passed by the electrons in unit time, that is this, and we are simply multiplying it by the delta V parallel, okay, which we will get from here, which we get from here, right? And so we're going to get the F. Okay, and yeah, so that's that. Okay, the ME comes from here, and so you have the delta V parallel, NIV, and D phi, and BDB right there. Okay, and when you plug in for this delta V parallel from here, remember these two dependencies. There's a B squared and there's a V cubed in the denominator. Okay, and there's a B here, right? And so B over B squared gives you a 1 over B. Okay, and V over V cubed gives you 1 over V squared. V squared doesn't matter. The integration is only over B. Yeah, and yeah. And by way of a remark, it's important to consider this remark that delta T is a typical interaction time for individual Coulomb collisions. Delta, so that's what they said. And it is approximately 1 over omega PE. We have not yet defined the omega PE. It's a plasma frequency. We will come to that. Okay, and that's a plasma parameter. We've not yet come to that, so we will defer. I mean, it's already assuming foreknowledge of what we're going to discuss right now. Right. So the thing is, the thing to keep in mind here is that the delta T is short in comparison with the time for a test electron to traverse a Debye sphere. And the time for a test electron to traverse a Debye sphere is something like lambda D over V. Okay, and if you substitute for this V with a thermal velocity, it's the reciprocal of a frequency which is called the plasma frequency. We will have right now. Let's not pay much attention to this. We will define the plasma frequency a little more precisely, maybe in the next lecture or the lecture after that. Okay. So just read these remarks. These are clever remarks, very important remarks. But for the time being, we can skip over them. And the point is, you see the B, right? Technically, the B goes, when you're integrating from time minus infinity to infinity, the B goes from 0 to infinity, right? As such. And so the dB over D, when you integrate from 0 to infinity, it is divergent at both its upper and lower limits. And here is the rub. This is the problem. Therefore, common sense, okay, so formally this is a mathematical problem, but we're doing physics here. We don't care about exact mathematics. We want a useful practical result. And so therefore, so this would be the low end of the closest approach, and that would be the farthest approach. Right, so with regard to B, the 0 would be the closest approach, and the infinity would be the farthest approach. Okay, so this is already giving you a bit of a taste of what we're going to do now. So we're going to replace the 0 by some kind of B min, if you will, and we're going to replace the infinity by some kind of a B max. Right? What would be a reasonable thing for this B max? Well, the Debye sphere, the Debye length, right? So the B max is the Debye length, because we know that beyond lambda D, the charge is screened. That was the whole point. So why bother about any B's that are larger than lambda D? So instead of infinity, we simply say, instead of the upper limit here, instead of infinity, we simply say lambda D. What about a B min? That's a little more tricky. There can be, the classical distance of, if you're doing classical electrodynamics, the classical distance of closest approach, one way of estimating it would be when the Coulomb potential energy becomes as large as the electron kinetic energy, like this. So in other words, the delta V parallel becomes comparable to the delta V perpendicular, and the scattering angle becomes large, 90 degrees technically, but we can just say large. Okay, so that would determine a minimum instead of the zero. What to replace with the zero? That would be a B min classical. Okay, there's also another way of saying of estimating a B min from quantum mechanics. What you say is B is less than half the radian de Broglie wavelength. That, okay, so that's another. So take your pick, whichever is smaller. Whether it's the quantum mechanical B-min or the classical B-min, you can take. So they both have very different temperature dependences. One has a T raised to 1/2 temperature dependence, minus 1/2 temperature dependence. The other one has a T raised to -1 temperature dependence. So there are those subtleties, but the important thing here, okay, the whole point of what we were doing all along was the fact that now this dB over d, this integral has a Bmin and a Bmax. The Bmax is just lambda d, and so and obviously, you know, the integration of dB over b is a logarithm, and so this is the all important Coulomb logarithm ln lambda, which is where the lambda is lambda d over where the capital lambda is lambda d over Bmin, where the B-min can be the maximum of the classical value or the quantum mechanical value. You don't have to be terribly fastidious about that. The B-min is some B-min, okay? But the B-max is what matters.